Hey, welcome back to the Cycle World podcast. I'm Mark Hoyer, editor-in-chief, and I'm with Kevin Kamen, our technical editor, who you may have heard of. Hope he makes it in this business. This week's topic is brakes, the evolution of brakes, where they came from, and everything we've used to slow things down, and how we've improved so much. Early brakes. I go back to my mini bike and go-kart days, and I had an upgrade from just a piece of steel rubbing on the tire with a lever pedal. Mine, someone had riveted canvas too, so I had canvas to sort of maybe help with my braking performance on the rear wheel of my mini bike and go kart. Not bad, not great,
Not great.
but we've used almost everything: leather and bands and rim brakes, and one learning from bicycle rim brakes. Not me, luckily, but they can get so hot with the friction on the rim that you can, pop a tire.
Yep.
So heat's important. You made a great observation, Kevin, that we take all of these molecular excitements from combustion and making them act on pistons and all of that. It was quite
rattle
good.
of the molecules.
The rattle of the molecules, making heat to make us go, and what do we got to do? Make heat to make us slow.
Yep.
So
the pads micro weld to the moving disc. The welds are stretched. Ping, they break. They weld again. Each time they stretch that piece of disc and let it snap back, that is heat. Molecular vibration in a solid.
Man, is that where we're starting? Molecules again?
No, let's talk about asperities, shall we?
Asperities, yes. We still have asperities fan mail coming in. We had an engineer write it, and he said he used the word asperities every day in his power drive. Shout out to you, Joe. Power drive, ag equipment, things like that, very precise hydraulic controls and so forth. Asperities was part of his daily life, as it is everyone's. They just don't know it. Okay, well, where do you want to launch this ship?
I want to make a couple of observations about the early motorcycle. The two main points. One is there were a great many ideas for how to slow a vehicle down. And you've just reviewed a number of them: rim brakes, scraper brakes rubbing on the tire, belt rim brakes, a block of friction material from Herbert Froude's Ferodo company, the friction material being made out of organic binder, horsehair, and who knows what, cornflakes possibly. But he started a company, Ferodo, still in business. Anyway, a lot of ways to slow a vehicle down. And the second point was, the main point about motorcycles in those early days was to make it go. And the idea of having to make it stop is sort of quite secondary. So it wasn't until, pretty much into the 20s that it became just as important to stop as it was to go. And the type of brake that had prevailed was one that exposed a hot surface to the passing breezes, the internal expanding drum brake. A pair of shoes faced with friction material were wedged outward by a cam acting on their ends to rub against the internal surface of a shallow drum. And the outside of the drum, as time passed, was decorated with cooling fins and all sorts of things. Holes were drilled. But it wasn't really until the 1930s that brakes became serious business, because if you arrived at the end of the straightaway on your single-cylinder Norton doing 125 miles an hour, you needed something besides shoe leather. And at one point, one of the Norton guys went out. He said, "I'm going to fix this." And he went out shopping, and he came back with several sets of Model T Ford drums. They were 8 inches. And that's when braking really got quite serious.
Well, I wanted to pause for historical context because you said, braking got serious in the 1920s. And if we look at the big picture, the period between 1900 and 1920 saw a massive change in how human beings moved around. If you went to a
Yeah.
big city in 1900, your biggest problem was stepping in horse droppings, and tons of it were being shoveled out of the city, put places, flies, all those things happened. And then by the 20s, trucks and cars and things were really happening, and by the 30s it was cemented. So yeah, we needed to slow down because we had invented traffic. And
Yes,
I
invented
just
it.
one observation I want to point out is you're not stuck in traffic, you are traffic. Just
Yes,
keep that in mind.
right.
All right, so yeah, the world had changed and we needed to stop. And that I you talked about the drum brake and its sort of rise to primacy, utility, Model T brakes on your Norton. But you had pointed out a fellow named Elmer Sperry in
Oh, yeah.
1898 made a disc brake. Why didn't it catch on then? They're so much better.
They're
I mean, I
just,
don't hate drums, but I don't like them.
I was so delighted to open the crate of TD2 Yamaha Road Racer in 1969 and find that it had that 250 millimeter four leading shoe front brake on it. I had yearned for such real, in quotes, brakes for several years because I tried to race a Super Hawk, and after every practice I had to take the brake shoes out and sand them because the organic binder, usually phenolic plastic, rose to the surface. My wife called that overheated brake smell burning pot handles.
It
They
is, yeah.
too are phenolic.
Yeah, I think I've had a few drum brake things in my life. I had a 64 Cadillac with four tremendously huge power drum brakes. I mean, they must have been probably 12 or more inches in diameter
Yeah.
and 3 inches wide probably. And they worked they really worked quite well if you were just tootling around, but if you really needed to stop, you got one. And even
Yeah.
then, if it was a long stop from a high speed with a 5,000-pound Cadillac, it was brake fade while you wait. You just you felt the pedal just same with the
It's coming.
Velocette.
It's coming. Yes.
Yeah, the Velocette. I have a 54 Velocette. In case you didn't know, folks, I had a Velocette. Still have it. It's over there. Um, those are initial brakes were not the full width hub. That's the one that people want later is the full width hub. So that the width of the hub is all braking on the inside of the drum. And this was just a little watch band, as I've said before, just about that wide, even possibly narrower than that. And not bad for tooling around, but end of a long straightaway, really got to get it done. Nope.
It's not. No, those early drums, many of them were press formed.
Mm.
And press forming, of course, puts a lot of stress into the metal and it stays there until it gets hot the next time. And then it relaxes into a shape that won't stop your bike. So not only did the drums open up like this from
Cone.
heating, but
He's making a cone shape. They're opening up because the side of the drum is material. It's the side plate, and that's going to hold the inner part of the drum, and then the outside is going to bloom like a flower. That the side where the all the mechanics go in, the open top of the bowl, so to speak, it just goes in and it blooms like a flower under heat. And as Kevin pointed out, that press form brake, you take this material that might be, if it's rolled, it's nice and flat, and then you stick it into a thing, and it's just got all kinds of different stress areas at a molecular level that are just waiting to express themselves, as you said, with heat. That's why we do stress reliefs and so forth, heat
I
treating.
visited the shop of Mac McConney north of Boston in the middle 60s. And there was Jess Thomas, who was a well known American racer in a certain era. And he was standing talking to Mac, the proprietor, and saying, You mean this whole thing is cast iron? No wonder it's so heavy. But they made those cast iron drums because they could stress relieve the casting and have a brake that would continue to work even when it was quite hot. So that was a step.
Yeah, poured to form. It was
Yeah,
poured into
into a mold.
a
And
mold,
yeah,
and then machined where you needed it to be machined, and away you went. And that was a step away from boing. you know?
yes. So in the late 1930s, the Germans were the pioneers of the full width hub. Earlier, the brake drum had been like a 6-inch ashtray or a pie plate that was bolted to one face of the front spool hub, and the backing plate was with the shoes was rode inside of this. And Vincent built their front brake as a dual drum. It had two of these pie plates, one on either side of the hub, um, in hopes of having more braking power to go with their large V twin engine. And the Germans, who had come through um, Bismarck's system of higher technical education, um, looked at the thing and said, why don't we make the drum the full width and lace the spokes onto the drum flanges, not bolt us all together out of lots of little foolish pieces. And that was a great step forward.
Yeah.
And the tremendous drum brakes of the 1960s on racing motorcycles that some among us revere to this day because of their extreme nature and their mechanical beauty. Eventually, people were using 3 different friction materials on each shoe. A leading shoe is a shoe that is self-servo acting inside the drum. The rotation of the wheel adds to the pressure pressing the shoe against the drum. So you don't want to put the ultimate friction material out at the tip where the multiplying effect is large. So they stepped this so that they could avoid the problem of having so much self-servo action that the brake would not release when you let go of the lever. That's been known to happen. So it was a sort of a high wire act and getting that to work just right. And the drum brake soldiered on in automobiles and production motorcycles. And meanwhile, in auto racing in 1953, Jaguar won the Le Mans 24-hour race with Dunlop disc brakes. And I remember the description was that here were the Mercedes cars with the big flap that opened up, lifted up behind the driver, an air brake. And they had tremendous finned drum brakes. And the Jaguar would come whizzing past them on the approach to the corner. The Mercedes driver is devoting himself to forcing the pedal to the floor. And this Jaguar comes by still on full throttle, brakes violently once, darts around the corner, and is gone. And people just looked at that and they said, well, that's over with.
Progress
Yeah.
has happened right now.
And they had been trying out disc brakes on aircraft. The F-8F Bearcat didn't make it to World War II as a carrier fighter, but it was given disc brakes. And the great thing about disc brakes is that since the friction material is being pressed against the disc from both sides, there's no escape. The disc can't get away. It can't warp away, subject to some explanation later. But
Yeah, there are rules.
yes, the thing that was so wonderful in '72, I brought my homemade 750 Kawasaki triple down to Daytona with one of those 250 millimeter Fontana brakes. So beautiful, so useless. And every lap, lose 100 feet into turn one onto the disc brake equipped bikes. And the disc brake couldn't come into its own until the slick tire became generally used from 1974 onward. So you had all this wonderful grip from the tire, and you had a disc brake that could absorb that energy without warping, fading, etc. So that was a period of rapid evolution. 1969, Honda came out with the CB750 that had a disc brake on it. And supposedly the background to that was that Yoshio Harada, who was big wheel on CB750, had spent time in the US and had seen a Lockhart disc brake, might have been for as a part of a spindle stopper system for machine tools. I'm not sure. Someone had adapted it to a motorcycle. It also happened on the East Coast with a different make of caliper. It was Bo Brinker that did that. He was a Bultaco guy. But Mr. Harada saw these things and thought, we must have this.
Yeah.
And so he went to Mr. Honda and he said, now we're planning to put drum brakes on this motorcycle, but here's a better idea. What must we do? And Mr. Honda said, disc brake on the front, drum brake on the back. Cover your bets. So that was the start of disc brakes on production motorcycles. In that same year, or maybe beginning in 1968, the late great Peter Williams adapted Formula Car disc brakes to his Arthur Matchless G50 called wagon wheels. It also had cast wheels, and showed that this was a substantial advance over the drum brakes that had been used previously. Now, bear in mind that one reason for the drum brake being successful was hard for water to get inside of it. It wasn't going to just fill up with water. External contracting band, rim brakes, all of those brakes were subject to loss of grip from water. But eventually, of course, they began to make pad materials that could deal with water, but that came later.
Well, I wanted to go back to drum brakes and kind of talk about the fundamental operation, since we kind of sped by into discs and that transition. Your typical drum brake of the 50s in your Triumph or whatever, it was a single leading shoe. And so you'd have a drum, you'd have your drum that's, pie plate or, spring-form pan for your cheesecake.
Yes.
And you'd have that, and then the mechanics would go in, and you'd have a single a cable would come down, it would pull a lever arm, and it would twist a cam inside, and the ends of those shoes would be expanded on the same end. So one side would have a self-servo effect, and the other would be the opposite. Anti-self-servo. Yeah. And you could do things to make those effective. People would lace their wheel and then skim the drum in their German submarine gap bed lathe, Kevin Cameron. Gap bed lathe just means you could take out the bed and you could put a big wheel in and spin it around and then get your tool in there and cut a drum round. And then you could surface your shoes in a similar fashion so that the whole thing would touch the drum. You wouldn't have the
uniform contact.
Yeah, you're arcing the shoe to meet the drum. But it was still, one servo, one anti-servo, and they were okay, but they didn't work that great. Double leading shoe would then be two shoes, and you would pivot so that you would pivot on opposite ends.
And there were two cams. Yeah.
Two cams. So you'd have a cable that came down, and then you got, linkage that would go across the outside of the drum, and it would operate the cams, and you'd have to carefully adjust that and and do everything to make it perfect for your race or your day-to-day, whatever you're doing. And then 4 leading shoe brakes, which, kind of, well, I mean, you said there was even 6 leading shoe, you said.
Yeah, one Italian outfit decided to just march on in the direction they were going.
It's like the pictures of 7, 8 valve Yamaha cylinder heads when they were 2 plugs and they had valves everywhere as they were exploring how much valve area can we fit into a cylinder and what good is it? And we found out 4 is just fine. 4 is good. And 4 leading shoes were really, that was probably the pinnacle of the drum. And in that case, you had linkages on both sides, and you had four shoes inside the drum, and all kinds of things to adjust, and maybe 2 cables going down.
Yeah.
And you had to make sure all that was tip top. You really, to get maximum even braking force, you had to adjust that stuff perfectly. You pointed out something really great about great big drums. So the drums grew to fill the wheel practically. Spokes went from 7 inches or whatever, something to little tiny stubs that kind of connected the rim very closely to this huge drum in the middle of the wheel.
I brought some. I've got a box of them up in the shop.
A little short, like 3-inch, 2-inch spokes, little tiny things. And making the hub out of the brake was a great leap forward. That was a great leap forward, but also you're putting the heat into the hub itself, and then you've got tiny little spokes that don't have a lot of spring to them. So what you're doing when you're lacing, the longer the spoke is, the percentage of change of stretch is, let's say you have more to work with on a long spoke, but in a short spoke, you put it under tension, there isn't a lot of stretch to it because it's just this long. 10%, they say, just call it 10%. 10% of 2 inches or 10% of 10 inches is a big difference.
Sure is.
So you'd lace your wheel up, and everything would be perfect. It'd be straight, and the spoke tension would be perfect. And then you just hammer it, into turn 1. And what would happen, like by the 4th lap or 5th lap, the drum would grow and wobble would happen. Your rim would no longer be straight. And crazy. I mean, I feel good about disc brakes. I do. I love a beautiful drum brake, and you can make them work pretty well. And people are racing with them in ARMA. People are racing with them in ARMA and having fun. And we like them on vintage bikes because they, typically your drum brake on your British motorcycle doesn't have brake fluid. Which, thank you, because bleeding, it's enough to keep up with batteries on these things, but also to bleed brakes.
Holes in your shirt.
So. Oh yeah, brake fluid.
You could always tell the setup kid in any motorcycle shop because he was wearing a T-shirt with holes all over it.
Yeah, brake fluid, folks.
Batteries.
Yeah, absolutely. And brake fluid will strip your paint and dye your or bleach your shirt, so you can take the color right out of a lot of clothing with some brake fluid. It's a great soap in small quantities with some hot water. You can actually clean a few things with that, but we digress. So yeah, it was drums were okay, but glad to move on.
And move on they did. Honda's first system, the caliper swung on a pivot, so that as the pads wore, the caliper sort of swung. It had a piston on one side and no piston on the others, which meant that as the shoes wore down, the caliper would swing. And that system didn't last. It was a sort of a first try affair. Kawasaki had a system with pistons on one side. Yamaha went to their cast iron caliper that came out on RDs in the 70s. It had pistons on both sides, and that caliper could be mounted rigidly to bosses on the fork legs. So that was something of an improvement. But those cast iron calipers weighed 4.5 pounds each.
Yeah, that's something. Well, you talked about Jaguar disc brakes, and I've spent a little bit of time working on those. And so what we have now are incredible, like the Brembo machine tools that they use to do these super exotic stylemas and all that. they a lot of times will have a single piece, and they stick the machine tool up, and it goes out and it machines the bore. So you have a caliper that's a single piece, and even if they're bolted together, they're these great big aluminum things or whatever material they're using, and they bolt them together with great big bolts, and it's it's beautiful, and it's quite rigid. And the early Dunlop disc brakes on Jaguars was a cast iron bridge, so it was like a horseshoe but lengthened, so to speak,
Yeah.
that went over, and then with four relatively small, the bolt heads on them are 7/16, four relatively small bolts on either side is the piston half that bolts to that with tiny little bolts.
Oh,
And like
yes.
on it, yeah, and on it, and then you stick this kind of Fig Newton sized food analogy, thank you, Fig Newton sized pad with a little slot in it so that it would also retract from the piston.
Mm.
The seals were in a weird spot too. The seals weren't in the bore, the seals were on the piston. All kinds of problems. They did work okay. I spent a lot of time making my factory Jaguar E-type brakes work as well as they possibly could. And what you would get is, say you're doing 100 miles an hour and you're coming up to a corner, and you first apply the brakes and say 20%, 20% braking force as you're squeezing down. You think, wow, these are really good. The car slows. And then you get to a point where you're adding a lot of force, and the caliper starts to deform, and all those four tiny bolts that are holding the pistons are going, oh, what are you doing? And it just kind of the feel, they're okay. I mean, they're certainly, they're heat durable. You can do that over and over again. It's just that, making the rest of the components very rigid, as we've seen with motorcycles, going to a radial master cylinder where you're squeezing against the handlebar. You're not doing it through a lever that's pushing in the same plane as the handlebar, or along the same axis as the handlebar, and then putting super Titanic brake lines on there that don't deform at all. Like a rubber brake line is going, it's inflating a little bit no matter what you do. Kind of, you put that braided line, and then you have a caliper that is knockout, and then what you get is your force. You're feeling the pads squeezing on the disc, and as you pointed out, the disc has nowhere to go when it's being squeezed from either side. And then you got really impeccable feel. And what we've done, what Brembo has done, and principally Brembo with the racing operations, there was a press introduction for the Aprilia Mille factory at Mugello circa 2003. Those brakes, that was the first time I'd experienced brakes of that caliber, and I was riding at Mugello, which is a good place to have good brakes. And there's a chicane at the top, and I went through the chicane, and I got a much better drive than I had ever before in my learning of the track. And I was like, oh, that was fantastic. And then you're going toward that downhill section, and I was like, oh my, I really was going in pretty hot. So I hit the brakes and I lifted the back.
Yeah.
Just like very quickly pivoted up, and I was like, oh no, but I still needed to slow down. And it was that step in modulation, the ability to release and still be braking hard, not release and then try to start braking again, but release and allow the bike to come back down,
to reduce
without going, ugh, that you could at enough braking force to lift the back of the motorcycle, then modulate it to keep braking hard, but let the thing get back down so that you could, hey, make the corner.
Yeah.
So it was great. I mean, it's beautiful the way, and it also, as you point out, tires, the way that, I had a time travel moment at my ARMA experience at Barber, racing twin front discs on a 1972 BMW with 75 horsepower. Really reliable, repeatable braking. Never changed for me through 4 days of practice and racing. Lever never changed. Good old brakes, and very good, vintage race tires. We're using these Connies with a race compound, narrow 90 something at the front. Perfectly great. Well, I just what I want to do is finish is going to then getting on a BMW M1000 RR, bookending the Superbike era. what an ass kicker. I mean, phenomenal. Lifting the rear wheel going into Charlotte's, just lifting the rear wheel and going, oh yeah, okay, this is what we're doing. And the fatigue that also brought because the forces are so much higher. But slick tires, 17s, full race rubber. Yeah, phenomenal
Good for him.
change.
Yeah. Well, on the way to the successful present day in metal brake discs, there were some difficulties. When superbikes, the 1000cc sit-up superbikes became a big deal from 76 onward, 76 through 81, 82. They had trouble with disc warpage, and Gary Mathers at Kawasaki decided that they would have cast iron discs made, and they would grind them flat and stress relieve them, and grind them flat and stress relieve them until they finally got discs of the desired dimensions that would absorb the heat without going all funny. That was one thing. On the other hand, my rider, Rich Schlachter, and I went to Loudon in 78, and Loudon has 10 turns in 1.6 miles. So there's a lot of, the engine is just basically turning the brake discs so that the brakes can get a hard time. And they did. What happened was that the brakes would become very hot, and they would stretch their rigid bolted connection to the hub, the aluminum hub, permanently. They would yield it. And then when the disc cooled, the hub would be too big and the disc would be too small. And so it would have to go out of flat. And in doing so, it pushed the pads back in the calipers.
Always a bad time.
Yes, at a bad time. And I got out the 12-inch straight edge and laid it across the disc. You could see it right away. It was just cone shaped. It was bad. And it wasn't all between the disc and the carrier either. It was also within the disc, because what was happening is the heat enters the disc more rapidly where the velocity is highest, namely at the OD, more rapidly than at the ID of the friction track. And those Yamaha pads were 2 inches in diameter, so there was a large radius difference.
Well, that was a big deal. Is that radially the friction area matched the pads, and as you say, it was like at 2 inches, and so the speed at the inside much lower than the speed at the outside.
So
and then
coning.
the coning, the heat, because it's hotter where it's going faster. There's more friction, and there were various strategies. Which go ahead. You tell us how you fixed that.
With my heart in my throat, because nobody likes to mess with brake discs, just as nobody likes to mess with gearboxes. I drove home 90 miles that evening, and I drilled or sawed radial slots in the disc, and they immediately became flat again because I had relieved that hoop stress. And at the end of the saw slots, I drilled a round hole so that the radius would be large enough that the metal wouldn't say to itself, that cracking's a great idea. I wonder what we could do with that. Let's go give it a try. And that's called stop drilling a crack. It's a familiar technique when you don't have enough parts. But then I beveled the edges of the saw cuts and brought the disc back. And in first practice, he had wonderful brakes. And they stayed that way. Well, what was happening, of course, was that tires were getting better, brakes were getting better. The rate of heating going into the discs was just extraordinary. And what came next was narrower discs carried flexibly on their hubs by means of driving pegs, little spools,
Buttons.
T-slots, all sorts of things to allow the disc to grow without having to pull the carrier with it. So that's why modern disc brakes have narrow pad tracks, because that minimizes the velocity difference between the ID and the OD of the pad track, so that the non-uniform heating does not cone the disc as much. And the flexible mounting, the floating disc mounting, is now universal. You don't see any rigid mounted discs anymore. It's not up to the work. So and away went pads that were 2 inches in diameter, because they saw that they had to go to a narrower pad track. And
Yeah,
in
they'll make
fact,
a long narrow pad because you're adding,
yes,
we're doing the 6 piston calipers and stuff. So you're trying to get the area for the pistons, just as you would put 4 valves in a cylinder. You want a very long pad, and it's you're going to get that by adding pistons, so the diameter of the piston can match this narrow braking area, and then
the width of the pad track.
you're
Yeah.
just distributing it along the radius to make your brakes work pretty darn good.
And then, of course, the initial pad materials were so-called organic, which means that they might have bits of metal in them, or ceramic powder or various stuff like that, but it was all bound together by organic resin, namely the same stuff that they make pot handles out of, which is why when you get organic brake pads or shoes extremely hot, they smell like a pot on the kitchen stove has boiled dry, and that resin is starting to give off gas. And of course, the gas is another thing. The gas forms a layer between the pad, the friction pad, and the friction surface. So you squeeze really hard, that gas comes boiling out of the organic material, and you don't have very good brakes if you're trying for ultimates. So that's where we got sintered metal or sintered ceramic pads. The sintered metal is sort of like what you can see on certain Ducati clutch plates. You look at them, you say, "Oh, that's copper on there," and then you get out your little magnifier and you look, and it looks like lots of little copper chunks that are somehow magically held together. It was powder, but it's been heated to the point that the little chunks are just sticking together. They're just bonded to one another. And that metal can make a wonderful friction material. The same thing with ceramic. The ceramic stuff, which is also sintered, is supposed to just shrug off rain. Don't need to worry about rain, because that awful scratchy pad material is going to reach the disc and do the job.
Well, what about so you're talking about the gases? What about giving them some place to go? Was that the meaning of cross drilling your rotors, putting lots of little Swiss cheese holes in
Well,
them?
there was a lot of theory put forward on that, but the original reason, Kawasaki's discs were 7 millimeters thick, and they were really heavy. So Steve Whitelock, who was Yvonne de Hamel's mechanic, saw that Indy cars had all kinds of holes drilled in their discs. So he went over to Dan Gurney's shop, the late great Dan Gurney, who loved to build things, including his strange feet forward alligator motorcycles. Whitelock went over there and they came up with a drilling pattern, and they filled those Kawasaki discs with 1/2-inch holes and made them a lot lighter. Lightness was their original goal, but people had started drilling holes in race car discs because of this gas problem, or theoretically a problem. And since that time, there have been all sorts of hole patterns and curlicues and wavy shapes. I would recommend, well, Mike Baldwin said, I choose my tires by walking over and seeing what's on the podium. And I would commend that to people who want their brakes to work exceptionally well. Try stuff, use what works. And now, of course, racing has moved on. MotoGP has moved on from metal discs to the carbon discs that first appeared on aircraft brakes. The first C5 transport plane, I think, had beryllium brakes. What's that smell?
Beryllium's not healthy.
And then they converted over to this carbon material, and which is basically a preform of carbon fibers which have incredible tensile strength. Now remember that old-time friction material had asbestos fibers in it. That was to hold the material together. The resin bonded it all into a whole, but the fibers were there to give it tensile strength so that it didn't just crumble away. So you've got this carbon fiber preform, and they fill it with organic material and it goes into an oven. And the organic filler gradually sort of calcines away until what's left is carbon, free carbon. And then they repeat the process as many times as necessary to achieve the density they want. And the reason they call it carbon is that it's carbon fiber filled with carbon. The preform is impregnated with carbon so that you get a solid part. And when our friend Gandolfi, who worked for Brembo, took me on a tour, he opened up boxes and took out carbon brake discs. He handed me one. It was, my fingers after that were covered with black stuff, just as if I'd cleaned out the pencil sharpener. And those discs in MotoGP are now nearing their limit. On the racetracks such as Motegi, where the braking load is tremendously great, even the largest discs, 355 millimeters, that MotoGP has as standard sizes, 320, 340, 355. They're becoming marginal. And some of you will have seen the recent photo of Marc Marquez's front discs in broad daylight glowing red. This is not a subtle effect, like turn off the lights, you can see it glowing. This is just too much of a muchness. What you would like is that the brake disc should operate between 250 centigrade and 850 centigrade. But clearly, on some tracks, they are exceeding that upper limit. And not sure what the result will be, but one of the things that has been tried is moving the fork legs farther apart by making wider steering head crowns so that the discs can be moved out from behind the tire's wind shadow so that there's a higher velocity of air passing over the discs to cool them. But how far does that go? Another thing that they've done is to extend the disc material inward from the pad track in the form of lots of little fingers. It's all sawed radially to produce a lot of surface area. Those are the disc's cooling fins.
Oh, my mountain bike brakes have those. My Shimano brakes have little inserts in them. They're wavy.
Yeah, well,
my road bike does too, for that matter. I got them on both. But yeah, because those are, you're with a bicycle, it's motorcycling taken to an extreme because you're dealing with my bicycle weighs maybe 19 pounds. And so that, and it's got to rely on my pitiful wattage and my great weight, 220 pounds with very low wattage output. So we're trying to make it light and strong and reliable. And so, yeah, we have those wavy things on our brakes, and they do work great. They are great brakes. I'd never go back to rim brakes on a bicycle.
No, rim brakes, brr.
Yeah.
Although Honda did resort to them in 1965 with one of their 50cc twin Grand Prix bikes, had rim brakes. And I think I haven't seen other examples of that same sort, but that was bringing back an idea from the early days when bicycles had rim brakes, and people thought, well, why don't we try them on motorcycles? And as long as the power was low and there was no consumer protection, they were a viable product.
Well, you might end up with a lighter wheel, because with a conventional front disc brake, your force is coming in at your 300 millimeters or whatever it is, 320. Yeah. It's got to go down to the hub. So that has to be strong to put the braking force into the hub. And then it has to go all the way back out through the spokes and out to the rim. So whatever those spokes may be, whether they're wire spokes or they're cast spokes, they are spokes. And so you had to make a wheel structurally capable of taking that braking force. And that was really one of Eric Buell's religious adherations.
Well, Eric is wonderful because he doesn't give up easily, and he'll keep on with an idea that everyone else is kind of going, man, can we just go home and get some dinner? But sometimes you discover something useful that way by just being very persistent, and nobody can question Eric on that score, because he was able to survive that relationship with Harley Davidson for years. And they, with their tradition of tradition, were not easily dragged kicking and screaming into the latter half of the 20th century by Eric, but he kept at it. And of course, his system was basically to say, we're not going to use the rim as the friction member. We're going to mount the disc, a large disc, on the rim. And then we're going to have an inverted caliper that fits inside of that large ring disc. Now we'll only need one brake disc, and it's at a very large radius, so its brake torque is high. And these are all points in its favor.
As is its velocity.
Yes, the velocity is high because it's farther from the center. But one of his former employees sort of winked to me after a lecture delivered on the subject of how good this single rim brake was. And he took me aside later and said, it's actually a really good brake on the street. It's only when you go superbike racing that you need something more. And so it's one of those.
Yeah, when they were racing with Hero and all that, they were having a tremendous problem with pads, and it took them a long time. My 1125 era, they had I want to say an 8-piston. It was the big caliper. It was kind of the next evolution of that front brake, and it itself had some sort of self-servo effect to it. And in testing, we were testing it. I think I was testing it versus an 848 or something. We were at Streets of Willow, and it was a challenge breaking it down to the apex, because you would make your brake application, and as you were coming down to the apex, it would basically apply more braking force on your behalf. So you just say you're pulling with 13 pounds or 12 pounds or 1 pound, whatever you're squeezing your brake lever at. If you held that perfectly, as you might aspire to.
Yes.
As you're going and you're releasing, as you're trading cornering for braking, you're releasing the brake so that you can turn more because you only have so much traction and you're using it more to turn and less to brake. The brake would continue to brake harder, even
Yeah.
as you were releasing. And it made it, that's a, everyone has a different tolerance for the feeling that you have trail braking. Don Kane is really, really good at trail braking. Like his ability to get it into a corner. Like if you want to find out where Don Kane smokes me and everybody else, it's the transition between upright and apex. And he was a devil at the apex as well. Like his lean angle and speed at the apex was very high, more than other riders. And that transition period where you are trading that cornering. So to have a brake be inconsistent, well, it was consistent, but it was unexpected and hard to control.
Yeah.
It just consistently would do that. And they worked on pad compounds and blah, blah, blah. And once they kind of reformed into EBR, those were pretty good. But then, the grinding process of this tremendous big disc that's, the diameter of the wheel, we had a brake disc on our test bike that was misground, and at the track it started to vibrate, and was there were a lot of challenges to it. In any case, so that rate, it was a good street brake. At that point, EBR, we got the new wheel. They shipped us a new wheel and we put it on that 1190, and it was a really nice street brake. It really was. But as you said, in racing, and when they had that Hero, they were smoking pads before the race was over.
Here's the reason behind it, and that is that you're essentially saying, okay, the motorcycle is approaching turn 1 at X speed, and we can figure out what its kinetic energy is at that point. You're about to apply the brakes. Then you brake down to the corner insertion speed and you figure out what the kinetic energy is at that point, a much lesser kinetic energy. And you subtract the one from the other to get the amount of energy that you're going to dump into the brake. Now, the lighter the total disc mass, the higher the brake temperature will rise during that energy dump, whether you're braking for turn 1 at Daytona or wherever it is. And it's very clever to try to make a lighter assembly, or one that steers more easily. Those are admirable goals. It's like when Yamaha adopted Adler's idea of a crankshaft mounted clutch. Oh, well, this will be great because we can make the plates smaller, because now the clutch is turning at engine speed rather than at gearbox input speed. So everything can be made smaller, but then you could only make one really hot start because all that energy of clutch slip would heat that little stack of 5 miniature clutch plates that looked like they were made for a motorcycle with a 30-inch wheelbase. And the plates warped and cracked. They turned blue. The friction material came off.
They did that with the YZ. Well, they messed with it with the YZF 600, which they called the Thundercat, circa 98, 97. And they changed the primary ratio and they spun it faster so they could make the clutch diameter smaller. And it was a pretty good clutch, but you could put a lot of heat into it.
Yeah.
And it couldn't take it.
Well, this is the same. The reverse problem happens with the brake. If you don't have enough mass in the brake, the temperature can go very high. And you can deal with that if you have friction material that can handle it, and if the disc material is not warping or developing hard spots at that temperature. But some engineering may be required. The other thing is that Yamaha had a problem with clutch start sometime in the first decade of this century, and they did exhaustive testing of friction material until they found a friction material whose grip did not increase with temperature. And what you were talking about, the brake continuing to brake harder and harder while you're trying to brake less, could very well be a case of a positive friction versus temperature coefficient.
Mm.
The hotter it gets, the more grip it has. And when you try to make a clutch that works that way, you're going to have a sudden wheelie and have to release, and you've lost the start. Oh, they're all in turn one, and I'm sitting back here. I think I'll read a book. So, again, these are details that engineers will have to open the handbook of chemistry and physics and call up their favorite friction material suppliers and start a testing program.
Well, something we've completely taken for granted during this entire conversation is brake hydraulics, brake seals. I mean, we talked about hydraulics a little bit, but we did not talk about brake seals in the caliper. You talked about molecular welding of pad material to the disc and stretching it and then letting go and re-welding. And yep, that's amazing. But the rubber seals, there's a lot of disco, well, we'll call it magic, a lot of magic happening with the rubber seals because that fineness of control possibly has a great relationship to how the seals are acting, how they grip.
Well, the thing is, the thing that you want is that the pads should retract slightly so that they aren't causing drag and horsepower loss while the motorcycle is rolling with the brakes released. So you want some tiny amount of pad retraction. But you also want the ability for the pistons to advance to compensate for pad wear. And what was found was that the surface finish of the bores in the caliper was an important determining factor here. That with enough texture, the piston would sit there and retract nicely, and gradually the lever would come down a little bit because the pad was wearing away, and then suddenly the lever would come back. What did that mean? It meant that the pads had advanced. They had overcome that grip that the seal had on the texture of the surface, and they had moved inward a little bit, and now they could sit there.
Testing data, real life. Triumph, I want to say Trophy 1200, way back, the early Triumph, like 95. I believe it was a Trophy 1200. The brake lever over time would just get softer and be farther from engaging the pads. So you had to pull the lever farther. And I complained about this in my road test back in Cycle News, and they said, "Oh, this happens." And I took it back to the guy who was doing the prep, and he was a very detail-oriented guy, really good mechanic, and he was doing the right job for his personality and jetting carburetors and all the stuff that he was doing. And he said, "Oh, here." And he goes over to the brake lever and he puts a squeeze on it, and he just squeezes it like he's holding the brake lever with both hands, squeezing it. And he does that for 15 seconds. And he's like, "Here, check." And he was advancing the pads. He was forcing the pads and the seals to get back into these. He says, "Just do that every once in a while." I'm like, "That's great, but can't we design around this so that I don't have to do that?" Like, I'm all for making things difficult in life, trust me. But yeah, let's just fix that. The opposite of that was Honda. I think it was 954. So the CBR 954RR. It was that or the 929. They put a coating on the pistons, like a low friction coating on the pistons to help with brake feel and etc. And what we found is that it also made them more prone to knockback being like a little bit of a wobble in the front wheel, and the brake, the pads are getting shaken back and forth, and just a little wobble on the 954, a little, would make the pistons. I think it was 954. Don't quote me, but it was of that era. It was sort of like 2002-ish, 3, 4, somewhere around there. And the pistons would knock back easier because they had some, I don't know, butter, Teflon, something low friction on them. And it would give you a surprise going into the next corner, because then you had to, push the pistons back to where you needed them to be to make hydraulic pressure.
Yeah. Well, it was a problem with some of the 600 sport bikes that if you went over a bunch of ripples that stress while the motorcycle was leaned over, the front tire, the front wheel might rock back and forth between the fork legs. And in doing so, the brake disc would push the pads back. And then you'd arrive at the next corner and the brake lever would come so far in that your heart would be in your mouth.
Yeah, Kevin's
So,
talking about deflection of the axle. Little spindly,
yes,
little tiny, weak ass axles, allowing
yes,
the wheel to the whole
to
fork
tilt
assembly
from side to side.
to
Yeah.
to tilt,
And
which
this
is
is why, first of all, GP bikes got great big front axles, 25 millimeter hollow axles in the front, whereas in the past, 14 and 17 millimeter axles had been considered normal and perfectly satisfactory. But with motorcycles, things creep up on you, and you've got all this tire grip that keeps working away at the problem of let's really shake up this motorcycle. Let's put forces through it for which it was never designed. Maybe if not this year, next year we'll get their attention.
but
And more
that's
engineering is required again.
which is what's beautiful about the progression of technologies. You say like, oh, well, why don't we just take disc brakes back to 1950 and put them on a Manx? Well, nope, because all you're going to do is lock the front and you're down, or you're
Yep,
going to flex the fork so much that, I mean, that's the beauty of what you were saying about Mark Marquez making his brake discs glow. It's we found the limit again. We're always
yep.
That's what's great about racing, because it just forces all
Keeps
we
pushing.
yeah, we got to rush around this track over and over again and see who can do it faster. and and people keep figuring things out, and the riders keep, you get a good rider. You take someone like me, and I go from a 75 horse BMW to 190 horse BMW with 50 years of technology, 55 years of technology behind it. And I spent the last 4 days getting my G forces and my brake feel and my feel for the contact patches all tuned up for a 75 horse 1972 motorcycle. It takes me a really long time to recalibrate. I still knocked off, 8 or 10 seconds over my lap times from the old bike to the new bike,
Sure.
but it is hard work. And you get somebody like a Marquez who is, or any of those guys, Moto America riders, like immediately, like, oh yeah, these brakes are better, and I get this lap time. Or you give them a tire, like watching. Even I saw the limit of Nicky Hayden's talent the first time he got during the Dunlop, when you could run any tire you want.
Yeah.
Jim Allen gave him a qualifying tire when he was early in his career, and he'd never had a really killer like the really good ones that last like a lap and a half. Like you get an out lap and you have to go right away because it's gone the next lap. Like
Yes.
that's where you could just turn the throttle.
It's like
Just
woolen socks, they go shrinking by.
yeah, and
The tire
I,
goes aging past.
I saw Nicky Hayden walking through the pit with his pie-eyed, walking toward Jim Allen, and Jim Allen said, "Let me guess. By the time you figured out how good it was gone." And he's like, "Yeah." Well, he didn't make that mistake again. It took him.
Nope.
That was the only session. But he only had a lap and a half, and
Yeah.
it took someone like me. I mean, I'll never, I'll never take it to the next degree, or to anywhere close to those guys. But you take a Marquez, and he's found the limit of the best brakes in the world
Yep.
on last year's Ducati.
Yes.
So it's beautiful. It really is.
So it is. And ultimately, what you're looking at is trying to make a ratio, the best ratio you can, between the force at the lever and the G's of deceleration that you get from the bicycle. And that can be, it's a good way to quantify how well the system works. And I tried using smaller master cylinders, and eventually I just got to a point where the springiness of everything in the system made the lever too bouncy, and I had to give that up. But Brembo's MotoGP and World Superbike calipers are designed using finite element analysis to put the metal where it can do the most good. Those calipers weigh 1 pound each, and they're good. They are stiff, and the lines are stiff. You were telling me about Honda saying, "Oh, we like to put the rubber lines on because the rider can feel the motion, the movement of the lever. I'm braking fairly hard. Now I'm braking harder." This was something that happened with early versions of the F-16 fighter. It had a side stick, and the original concept was that the stick would be immovable and the system would measure how hard you were pushing it in whatever direction. But pilots did not adapt to that. They liked to have some movement. They wanted to feel the stick move. That helped them to gauge how much effort they were putting into the stick. So this concept of production bikes having softer lines may have a basis in fact. For racing, it's important that everything in the system be pretty rock solid. And shall we pass over the terrible problems of bleeding brake systems?
Oh
The
boy.
ultimate is, of course, when you're in the midst of this and you've ruined the paint job and you've ruined your clothes and you've got brake fluid all over the floor, and you're saying to yourself, I'm going to build a swimming pool and fill it with brake fluid. Then I'm going to take all this stuff down in that swimming pool, holding my breath, mind you, and I'm going to assemble a system with no air in it. Actually, it's possible to do it without the swimming pool, but it can present problems.
Well, yeah, I mean, you could take the nice thing with a motorcycle front brake system is it really isn't that, I mean, for your average race bike, it's not complicated if you truly needed to take it completely off the bike. And then you could put the calipers at the top. You could hold the calipers up and you could bench bleed and get your air out the top. And that'd be one way of solving the problem. Another
Put
way
a
of
piece of
solving
sheet metal in each caliper to take the place of the disc. Yeah, that works.
You could do that. One of the other solutions. Yeah, one of the other solutions that I don't like is bleeding from the bottom. If you have an immaculately clean system, you can force fluid in from the bottom and fill the master cylinder from the bottom. So you put it in the caliper. But since I work on a lot of really crusty old garbage, what you want to do is get the garbage out. So I usually drain. If I have a hydraulic seal, if I have no air, basically no air in the system, and I just want to renew that, I will get a bulb syringe or I will get my, vacuum thingy bob, and I will vacuum out the reservoir and I will fill it with fresh fluid, no air this way. And then I will bleed it until clear fluid comes out. And I'll do that again until I don't get any trash, any visible trash coming out. And but boy, starting from broken lines and air, I tend to rely on gravity to do the first round for me. It's just fill it up, open the bleeder, and just kind of stand by, have a cup of coffee, wait for it to drip, 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 drip. And you can get a long way with gravity bleeding on cars too. Cars and my pickup truck. Well, thanks for listening, folks. We're putting the brakes on the show. Ooh, ow, sorry. Terrible wear. Don't do that. We appreciate you listening. As ever, this episode is brought to you by Octane Lending. There's a link called the Prequal Flex. It's down in the description. Click on that link. Check it out. If you're shopping for a bike, you can shop. You can see what your buying power is. You can get a real offer from Octane Lending that you can take to the dealer. You can be qualified to buy and have the buying power before you even walk through the door. So go ahead and click the link and check it out. Thank you for listening. We're really enjoying our time with you. Appreciate it.